Good evening, everyone. Welcome to the March Virtual Star Party. I see people are filtering in, so we'll give them a little bit more time before we jump into the fun things we have in store for tonight. Welcome, welcome, everyone. I'm glad to see you all here. If you know you have any questions, go ahead and put them right into the chat. We'll give everybody about another minute or so as people keep coming in. I'm glad to see all of you tonight. My day has been really well, thank you very much. I went out for a very nice walk this afternoon. I hope your day was well as well, and you're able to enjoy the sunny, nice weather we're having, at least yesterday and today. Got 2 days in a row of taking a walk. Okay, well, we're still coming in, but I do want to say welcome to everybody if you just joined us. My name is Sarah. I am your host for this evening. We have plenty of staff behind the scenes who are working to help this evening run smoothly. And before we go any much further, I do want to say that as a museum, we here aim to advance our collective understanding of both the Earth and the sky. And I would like to acknowledge that the Bell Museum sits on the traditional treaty land of the Dakota people. I would also like to acknowledge the Ojibwe people, traditional keepers of the lands to the north. Dakota and Ojibwe knowledge systems are crucial ways of knowing this place now called Minnesota. And we here at the Bell honor that knowledge, the values embedded in it, and the people who keep it. Now, questions are my favorite part of the night, so please, please, please use the Q&A feature in Zoom to send in your questions and comments through the evening. Amongst me and Thaddeus, who's up on the roof with our telescopes tonight, we have another member behind the scenes answering questions too. So we'll try to get to as many questions as we can tonight live, but we'll also get to some of those questions written in typed into the Q&A box as well. So we'll try our best to get through all questions this evening for whatever you might be wondering about. We also have live captioning tonight. So you'll see that on your Zoom screen. There's a CC button kind of on the bottom menu. If you find those captions distracting or not useful, you can go ahead and hide them by clicking the live CC button on your screen. So those are kind of some of the housekeeping things that I want to make sure everybody knows about so we can have a wonderful time here tonight. And of course, like all of our star parties, this program is being recorded. So if you miss any of it, you can always go watch the recording that will be posted within a few days here to our YouTube channel. I see some questions already coming in and they're wonderful, but let's get going at seeing what is up in our sky. And to do that, we're going to start with our star map because the sky is always changing. And we're actually in one of those seasons where it seems like the sky is changing a lot. And that has partially to do with daylight savings, which just happened last week. So if we look at our star map here, we can see that it is that whole circle. And that's because when we step outside and we face a direction, if we were to stand still and look in all directions all the way around us, our horizon line, our view of our horizon would be a circular around us. So by looking at our star map here, that outer circle is our horizon. Well, if the outer circle of our map here is our horizon, if we were to stand outside and look straight up, that is called the zenith. And that would be the very center of our map here. So the closer things are to the center of our map, the closer they are to the zenith straight above us. And then closer to the outer edges, the closer to the horizon they are. And with that, we can see that some of our winter constellations you're maybe familiar with are starting to set over in the west, kind of like Taurus. We can still see Taurus out in our sky right now, but Taurus is a winter constellation. So we're going to be seeing him set here in the next few weeks. But over in the east, we see the constellation of Virgo rising. We can see the bright star Spica just above the southeastern horizon here on our map. So Spica is a really good star to know, and it'll become easier to see as the spring goes on. But one of the things also that changes quite frequently, or quite quickly, I should say, not only are the stars changing in our sky as the seasons go on, as the Earth continues to orbit the sun, and then that daylight savings time kicking in here. It's a shift in when we can see the constellations when it gets dark out. But you may notice that Mars appears on 2 different locations of our map here. So Mars over kind of further west is where it is in the early part of March. But as we go through March and into April, you'll see that Mars, through this dotted line, actually goes from kind of the western side of Taurus, and will actually by April end up in the constellation of Gemini. Now we're going to have a chance, hopefully, here to see Mars through our telescope when Tad's up on the roof ready for us. So we'll talk about Mars. There's some cool stuff that was a little bit left over from last month. We can talk about exciting thing that happened last month is a Perseverance landing. But I see a question coming in from Kira. So let's start off the night with some questions. This is wonderful. Do stars have anything to do with how we change our clocks an hour ahead in daylight savings time? No. So we do, in fact, set our clocks by the position of the sun. So for instance, we'll talk about this later too with my handy dandy demo. We set the calendars by where the sun is in the sky. That's how we know when the first day of spring is, or the first day of summer, winter, or fall. And when the sun is overhead, we call that solar noon. That would be when your shadow is the shortest. Now, daylight savings, however, is a human-made concept. And that was to help us, I believe, save energy way back when. Is so that way there's more sunlight during the times we'd be awake during a normal work hour or work day. And so that's why we have the concept of daylight savings. And not all states follow it. And not even all parts of states follow. I think some parts of Indiana follow it and some parts don't. So half the year Indiana's in the Eastern time zone and half the year it's in Central time zone. So daylight savings is a completely made up concept by humans because it served a more purposeful role in our lives a good number of years ago. Now it just makes me want to sleep in later and my sleep schedule's all screwed up still even this week. But we do set our calendars by the position of the sun. And so time does have its roots in astronomy. And so that's kind of one of the fun things, because as we look over at our star map, Spica over here in Virgo, we see it rising here early in the evening. And that told farmers it was time to plant their fields. When they saw Virgo, kind of imagine the head and the body and the legs and the arms coming out, and Spica's at the end of one of the arms. When farmers would see this constellation rising in the east as the sun was setting in the west, they knew it was kind of March time like we see tonight. It was time to plant their fields. But as the year goes on, Spica is going to be higher and Virgo is going to be higher in our sky, kind of mid-spring. And then towards the summer and end of summer, Spica is actually going to move over kind of where Taurus is right now. And so that told farmers when it was time to harvest their fields. And so stars traditionally historically have played a role in telling time, not just on the day-to-day scale, but on seasons in the whole larger calendar scale of things, but nothing to do with daylight savings. Okay, another question came in. Is it just the Northern Hemisphere we're looking at tonight? Yes, because we live in the Northern Hemisphere. I don't have any live telescope connections to anything from the Southern Hemisphere. But they have evening right now as well if they're in the same time zone. And for the most part, you would see different things if you lived in the Southern Hemisphere. But we're up here in the north, so we'll stick to the northern skies tonight. Okay.
One thing
yes.
that would be the same. There I am.
Hi, Tad. How are you tonight?
All right. So I'm just gonna stop your screen share there.
Go for it.
And I am going to share a view of our moon. So this is a view coming from, you might have actually seen that image before. In fact, you know what? I'll just switch it and we'll shine a light maybe on the telescope. Maybe that'll help. So Megan up here is acting as a spotlight tonight. We are looking at the moon through our 102 millimeter Astrotech refractor. Fantastic little scope. I love this scope. And our ZWO 120 millimeter camera. And this is a live view of the moon that I hope you're all seeing. I hope I shared the right screen.
Yep.
And you can tell it's real because I'm actually moving the telescope and things are moving. And I can change the exposure and we can see that things will be brighter, things will be darker, and so forth. So this is the moon you'd see if you walked outside right now. It's a beautiful, cold, clear night. And this is the moon they'd see from the Southern Hemisphere. It's our moon. It's our Oh, we're good with the light. That's fine. But so Sarah, I guess I'll let you talk about the moon. Or I mean, we can stare at it for a while. I like the moon.
No, keep it on because that's a great example. So right now, we're just about to the first quarter moon. So we're seeing it kind of looks like on the image right now, the camera is adjusted such that the moon, the part of the moon that we see is kind of on the bottom of our image. But if you kind of turned it, if you imagine turning your head or turning the image a little bit 90 degrees counterclockwise, we would see outside, if you look outside your window, that's probably the easiest thing to do. We'd see the right-hand side of the moon. And that's what we see here from the Northern Hemisphere. Now, a few years back, it's actually been about 6 years or so since last time. There we go. So Tad's just rotating the camera up in the eyepiece of the telescope. So this is a little bit more like you can see if you step outside. However, about 6 years ago, it was the last time I was able to travel to the Southern Hemisphere. And it's really kind of bizarre in a fun way because it is a different sky, but they see the same moon phase as we do at the same exact time because there's only one moon and we can see at the same time. However, because you're on the Southern Hemisphere, you would see a bunch of us astronomers down there and we'd all be standing with our heads tipped back and kind of hanging upside down because our first quarter moon that we're used to seeing with kind of the lit side here on the right-hand side, because you're on the other side of the Earth, on the Southern Hemisphere, it looks like it's on the right-hand side. And so it kind of flips it and it's a little goofy and it's slightly disorienting. It's like, wait a second, I thought we were in the first quarter moon, not the third quarter. And so we have a bunch of astronomers down there and people who are really, really into astronomy and know their moon phase. It's like, this doesn't look quite right, but it's because we changed, not the moon. And so there are some things that are shared between the hemispheres, like the moon, but they look slightly different. Another thing that looks slightly different is Orion. So if you know Orion, he has 3 stars in a row for a belt, 2 stars for shoulders, and 2 stars for knees. Here in the Northern Hemisphere, we kind of see him right side up, with his head and his shoulders closer to our zenith. But again, in the Southern Hemisphere, when you're down there, everything's kind of upside down. So you see Orion with his feet in the air instead of his head in the air. And so it's kind of the fun things to look at something that's so familiar, yet from a different perspective, it does look very, very different. But you know what you're looking at. So that's kind of a fun thing. Okay, Terrence, yes. Your question is there a telescope on top of the Bell Museum? And that is exactly what we're seeing through Tad's screen up on our roof. Is he has cameras up there through our telescopes here live at the Bell Museum. If he talks, maybe you'll be able to see the setup there in the little icon.
Speaker. Oh yeah, they'll probably need to. So hopefully my video spotlights now, and hopefully you can see that I'm shining a light on the telescope. Yeah, Megan, one of our students up here helping me out tonight. Thank you, Megan. Yeah, so this is our telescope that's looking at the moon right now. We have another telescope set up as well that is on a star cluster that we can get to. By the way, sorry, the tablet died, so we're doing this. We're doing a lot of screen sharing from the one laptop tonight. But yeah, so these are all live views as much as possible. We may have some different images we bring in just to supplement things here. I'll say if you were seeing the moon moving around a lot there before, that was me focusing the telescope, trying to get it to be in focus. It's a little finicky. For those who do astrophotography, this telescope, forget the exact focal ratio here, but it's got a small focal reducer on it, so that makes our focusing a little tough.
Well, before you change, before you move away from the moon, we have 2 moon questions that came in right now. One is, what are the circles in the moon? And so the reason why I love looking here at the first quarter, something that's near the first quarter moon, is we can see all these craters. So those are all those circles, all those dents on the moon. And during this first quarter phase, when we only see part of the moon, we're getting some really nice shadows in those craters. We can see a lot more detail than if, say, the moon was full. If the moon was full about a week or so from now, excuse me, there would be so much light coming off the moon that it would wash it out. We're not going to see these nice details of the craters, the surface of the moon here. So that's why I love looking at the moon here in this first quarter phase, when it's not full, but we can see what's called the terminator, that line that separates day from night here on the moon. I see another question coming in from Jackson, who is 9, wants to know if the moon is colder than the Earth. Yes and no. Now the moon here, if you look at it, can't see any clouds. There's no trees or rainbows or anything like that. there is no atmosphere, there's no air on the moon. And that actually does something for the moon. It makes it so it can't regulate its temperatures and even them out. Here on Earth, we have a nice atmosphere that we breathe air in all the time, but that atmosphere actually helps kind of even out the temperature across the Earth from day or night. So here on Earth, the average temperature across the entire globe is about 60 degrees Fahrenheit. Now on the moon, without that atmosphere trying to hold in some of the heat and kind of even it out from day to night, on the daytime side of the moon, when the sun is shining nice and bright on the moon, it can get hot. I want to say like 300 degrees hot when the sun is shining directly on you. So it gets very hot. But as soon as you get over into that night side, that kind of darker area of the moon here that we're seeing, without that air kind of trapping some heat and kind of regulating it, it can get cold. It can get like negative 100 degrees or colder, if I'm not mistaken. So the moon is both very hot and very cold, depending on if you're sitting in direct sunlight or not. And that's because the moon does not have an atmosphere like the Earth does. So we're gonna be seeing a lot of cool stuff tonight. So we're not really focusing on any one thing in particular. We're looking at the moon because it's nice and bright. And it's here through our telescope right now. Tad's gonna show us a few other things as he moves telescopes throughout the night, but we'll answer questions about anything you're wondering about. There's no set agenda for tonight. It's just a fun conversation of what's out tonight.
Sarah, did you talk about the rays on the moon?
I have not talked about the rays coming off the moon or off those craters. But there was another question that kind of came in about the moon. What are those dark spots? Do you want to talk about the dark spots and the rays?
Yeah. So actually, I focus, or I'm zooming in a bit on one of these rayed areas, and they're a great contrast to these dark areas. Both, like, literally, one is pretty bright, the other is pretty dark, and they're also contrasting in age too. What I really loved about these rays that we see, you can sort of see the faint lines coming out from one of our craters here, is that these tell us that this impact threw out material, and it threw it out pretty recently. So the brightness of the area means that the regolith there, the rock on the surface, it's been overturned recently. You can think if you've gotten a chance to do any gardening here, or just cleaning up the yard in the past few days or past week when it's been sunny and warm, that soil that you overturn is a very different color. And that same thing happens on the moon when rocks and when impacts happen. So the existence of a rayed crater means that there's a fairly young impact. On the other hand, these dark areas, they're also massive impacts. They're called maria. And the maria, or the seas on the moon, are areas where massive impacts happened billions of years ago. And this would have been shortly after the moon formed, actually, when it formed from a impact between the Earth and another body. And so these maria reflect areas where the crust of the moon, the young moon, broke open and magma, lava welled up from below, and it covered the surface. And then it cooled down into this dark basaltic rock, this dark volcanic rock. And it's remained that way for billions of years, but we can still see, even in these maria, there are little craters still visible here. So these have had impacts happen as well. Fairly small ones, I'd say those are probably in the order of, I don't know, maybe 60 miles across, to be able to sort of see them right now, maybe a little bit smaller, 50 miles or so. But yeah, so these bright areas and these dark areas are very contrasting in what you can see. They're great things to look for if you grab a pair of binoculars. It's nice, they stand out nicely that way. And then they're also just contrasting in their ages too. You can see a nice little rayed one here. Most of these major craters do have names. If you want to know the names of them, you're gonna have to ask someone who's not me. I'm horrible with remembering all the names of the maria. I believe this in the craters. This over here, the nice circular one, I believe, if I got the angle right, is Mare Crisium. The Sea of Crises, I think, is that right, Sarah?
That sounds correct as far as what the name you gave it. I as well don't remember all the names of craters and the Maria on the moon. There's just so many of them that I don't bother memorizing those.
Yeah. All right. So what I'll do is I'll try to switch to a different telescope here. We'll do this little visual thing again, just so you can see what we're seeing it through. This over here, you can see Megan holding a light for us. We're looking through a Celestron 9.25-inch telescope. And we have a ZWO camera as well on the back of this one. And we're gonna see if I can get the right screen again.
Okay. There we go.
All right. So I've lost a few things here, but so I don't know if you've read up on NGC 2362 or if you'd like me to talk a little bit about it.
As you get settled here, there's a question that kind of relates to stars here as we're switching from the moon over to these stars. So a question coming in, why do stars have a twinkle when you look at them in the night sky? Well, we probably won't see it here through our camera views, but you can definitely see it when you look up at the sky and when you look at the moon or Mars, which is fairly close to the moon tonight as well. It's just a little kind of orange dot just off to the right side of the moon tonight. We're looking at a group of stars here. This is an open cluster of stars. Now, the reason why stars twinkle, or why we sing the song Twinkle, Twinkle, Little Star, is because stars are so far away that the light that's coming in from them, if you think of light as just this little, like a little tic-tac, if you will, one little piece of light at a time, it's coming from very far away. As it comes through the Earth's atmosphere, again, here's where the atmosphere comes in. It comes through our atmosphere, but there's molecules, there's oxygen and nitrogen. Our atmosphere is made up of lots of different gases. So it comes through this little piece of light and it'll kind of bump between the molecules in our atmosphere. And so because it doesn't come straight through the air, it kind of bumps around between the atoms, the molecules in our atmosphere. That's what makes starlight look like it's twinkling, is we're eventually seeing all that back and forth movement as that piece of light goes from the top of our atmosphere all the way through to meet our eyes here on the ground. So stars will appear to twinkle because of our atmosphere. Now you might be scratching your head, well, if it's all just our atmosphere, why does the moon twinkle? Right? The light from the moon has to come through our atmosphere as well. Well, the moon is a lot closer to us. And so instead of like getting one piece of light from that star that's really far away, we're getting like a 10-gallon bucket full of pieces of light from the moon all at once. And so instead of getting one piece of light from the moon at a time, or one piece of light from a star at a time, it's like taking that 10-gallon bucket full of all those little tiny tic-tacs of pieces of light and just dumping them through our atmosphere at once. It just comes streaming down. All those pieces of light just come streaming down all at once, and we perceive a nice solid column of light, a nice steady column of light coming from things that are closer to us, like the sun or the moon or our planets. That's why planets and the sun and the moon don't appear to twinkle in our sky, but stars, which are much farther away from us, do appear to twinkle. Is just because that light, it's how much are we getting at any one time and how is it making its way through our atmosphere. Okay, yes, so a question coming up here is about our seasons. We are going to talk about our seasons here in just a few minutes because I think I hinted at it earlier about how we see different constellations during different seasons. So hang on just for a few more minutes. We'll talk about seasons next after we're done talking about this cluster of stars, which, Tad, you called it by its catalog name. Is this the Rosette Nebula?
No. I'll look that one up and see if we can get that one later. This is also known as the Tau Canis Majoris cluster, because the bright central star is Tau Canis Majoris. Clever, I know. So slightly different. So not the Rosette, but it's I'm gonna guess, as with many open clusters, probably very similar. We've got about 100, maybe 200 stars here altogether. We're not seeing every single one of those, of course, but we've got a good selection of all of them that are visible. And this cluster here is pretty well aged for a cluster, 100 million years or so plus. So well into the middle stage of a open cluster like this. And it's located in the constellation of Canis Major, which is where the name comes from. Tau Canis Majoris is related to the Canis Major constellation. And it's actually just a little bit below the star Sirius. So
I'll switch back over to the star map so we can see this here, but then we can switch back over to the live view. So let's see where our telescope is actually pointed at. Let's go back to our star map. And so we see our star map, Orion, which is a familiar winter constellation. Let's use the belt of Orion here, those 3 stars. And we're going to draw a straight line, this time kind of down towards the south or the east. That's where we're going to hit Sirius. Sirius is the brightest star in our night sky. And that's at the heart of Canis Major, the big dog. And so Tad just said the cluster of stars that we're looking at is just kind of below here, kind of in the front leg, if you will, of the big dog. So that's what we're looking at.
I'll give a little bit better direction there. Actually, it's below is a bad direction, right? I should say it's to the south and east, above, below Sirius, and really sort of straight up from that hind legs of the dog.
Gotcha. So we're
So
kind of
like
over.
right there.
Okay.
Yeah, excellent.
Okay.
You see
There
what
are
I'm saying?
several clusters in this one, but yes, that makes sense that it's over kind of by the tail of the dog, above the hind legs. Okay. So that is where we're looking. Tad, let's switch back to that live view, because as much as a star map is helpful, looking at the live stuff is way more fun and interesting. So as we're switching back to the live view of the star cluster, Colton wants to know how hot stars get. This kind of ties into what Tad was just saying about how old this star cluster is. Stars come in all different temperatures, and that tells us they're all different colors. The color of a star will actually help us figure out how hot it is. And that in turn helps us figure out how old it is and how long it will live for. I saw another question not too long ago about, do stars eventually die? And they do. They run out of fuel to burn, and they will eventually die, or again, run out of fuel. So this one, I think Taddy said it was a couple 100 million years, and that's that's kind of middle age-ish, but it's still fairly young for stars. To compare, our sun is a middle-aged star. It's a middle temperature star. That's why we see kind of that white yellow in the sky. And I think the surface is about 10 million degrees Fahrenheit. And that's just the surface of our sun. And so our sun is a middle-aged, middle temperature star. As our sun and as these stars here in this open cluster age, they'll use up their fuel, and eventually they will cool down. As stars cool down, they'll go from being kind of that, our sun, which is a yellow, white yellow star, it'll cool down to being kind of an orange, all the way to being kind of a red star. Now, stars that are hotter than our sun are when stars are first born. A lot of them are going to be so hot, they're going to be blue. And so if a star is hotter, it's going to burn bright blue. And so that's kind of the fun thing about, I think at least, star lifespans and how their colors can help us figure out what temperature they are, and in turn, how long they're going to live for. So stars, if they're really big, can live for maybe a couple million years, maybe around the billion-year mark. But if it's a smaller star, it doesn't use as much fuel as quickly, it can live for billions and billions and billions of years. So our sun, average size star, average temperature star, will live for about 10 billion years total. And right now it's only about 5 billion years old, so we're only middle-aged. How big is the average star? About our sun. So we measure things in space by kind of comparison. So one solar mass, if there's other stars out there that are about roughly one solar mass, that means it's roughly the mass of our own sun. Stars that are much, much bigger, like 8 times the sun, that'd be like an 8 solar mass star, and those are gonna be like the super big ones, and anything bigger than that's gonna be like the super big stars. How big can stars be? Oh man, I forget the exact number of this one, but I think is it VY Canis Majoris? That's the biggest known star at the moment? Or is it the, I can't remember the name. VY Canis Majoris was the biggest known star for a little while, but I feel like there's one Scooty that just took, or that in the fairly recent years took over as the largest known star. VY Scooty, thank you. Hannah's in our background. She's one of our kind of astronomy experts here helping us out tonight. VY Scooty, or UY Scooty, is 1,500 times larger than the sun, and that is the largest known star currently. So stars can get quite big. Just imagine 1,500 suns in the middle of our solar system. Okay, let's go talk about seasons. So I'm gonna take the screen here, Tad, because seasons have to do with stars. They have to do with our sun, and so we're gonna talk about our seasons, because the first day of spring is coming up here, I think on the 20th. So I think it's what today's the 19th, so it's tomorrow. So why did we have daylight savings last week, which we talked about daylight savings has nothing to do with stars, but yet tomorrow, March 20th, the first day of spring has everything to do with the astronomy and the sun. So what's going on here? So I have my handy dandy display here. I hope you can hear me. This is not to scale. If anybody is wondering, this is not nearly how big the Earth is compared to the sun or how close they are. But we have the sun here and we have the Earth here. Now, you're probably used to seeing a globe, and that the globe of the Earth is not straight up and down. It's kind of tilted, and we can see that tilt here. where the North Pole of the Earth right now in my model is kind of pointed towards the sun. If we were to take this line and extend it out, it's kind of tipped towards the sun. And this happens on the first day of summer, is when the North Pole is tilted towards the sun. But another cool thing about our North Pole is it's pointed towards the North Star. That's why we call it the North Star. It's Polaris. It's at the end of the handle of the Little Dipper. But watch what happens. As I speed through time, we'll see the Earth rotate on a daily basis. You can kind of see it spin there. I don't know if you can see, but there's a little pin here. That's Minnesota. But as the year goes on, Earth is going to spin, but then this North Pole is going to be pointed at the North Star all year long. And so let's go ahead and watch the year go by. So the Earth is now made a quarter of its way around. It started here at summer, and now it's made a quarter of its way around. And you can kind of see how the axis is still pointing the same direction. It's just it's not pointed directly at the sun because we've moved, but it's not pointed directly away either. It's kind of in that in-between. And so when the sun or when the Earth has moved, so that way there's equal parts of daylight on both sides, we'll get equal parts day and night. So that's our equinox. So that's our spring equinox. The day will get equal parts day and night based on where the Earth is around the sun. Now, if we continue watching the Earth orbit the sun, you can now see it's halfway from where we started. But this time, the North Pole is still pointing at the North Star, but this time it's pointed away from the sun. It's tilted away from the sun. So this is when we get winter up here in the Northern Hemisphere. When our North Pole is pointed away from the sun, it's winter. If we keep going, kind of from that viewpoint, I'll tilt a little bit, we can see the North Pole is still pointing the same direction, but we're kind of that halfway point from where the North Pole isn't pointing completely away from the sun, but it's not pointed completely towards the sun either. So this is another equinox of ours. And so actually in this case, this would be the spring. So we just came from winter when we were tilted away from the sun. Now we're kind of halfway. And then we can complete the year until the North Pole gets back over here, or the Earth gets back over here, and our North Pole is once again pointing towards the sun. So that's one whole year. And it has to do with where the North Pole, how the Earth is tilted in space. Now, I'm going to share we're going to share a fun link to seasons in the chat. And we're going to simulate this because what's fun is that the Earth is not the only planet that's tilted. So I'm going to share my screen here quick, and we'll put a link in the chat. So we can see an image here of the sun in the middle, and then we have the Earth and its axis, that black line. So when the northern hemisphere here, when our northern axis is tilted towards the sun, we have summer. As the Earth moves around from summer, where we're kind of halfway here, we have fall. When we get all the way over to the other edge, when the northern hemisphere is tilted away from the sun, we have winter. And then halfway between winter and summer, where you get another equinox, equal parts day and night, we get spring again. But the Earth's not the only planet that's tilted. Here on Earth, we're tilted about 23.5 degrees. So we're not straight up and down, we're just ever so slightly tilted. But if we look at the other planets, Mercury is pretty much perfectly straight up and down. And then Venus is almost completely tilted completely over. So instead of the sun rising in the east and setting in the west, the sun on Venus rises in the west and sets in the east because its tilt is almost completely opposite ours. And you can see here that Mars isn't too far different than Earth's. Jupiter and Saturn, Uranus and Neptune each have their own. The fun thing about Uranus is it's not straight up and down. It's not upside down like Venus. It's almost tilted sideways. So we added a link to the chat there. And that's going to be kind of fun because if we go to that website, I'll share my screen again. We can play around with what would happen if the Earth was tilted at those different degrees. So we have several different areas here on the screen. This is kind of Earth's default. If we look over on the right-hand side, the Earth is tilted in real life 23.5 degrees. But what if we tilted it to 0? What if the Earth wasn't tilted and it was straight up and down? Let's see if I can get this to 0. There you go. And then we could see what would happen to our seasons. Essentially, we'd get the same amount of light at any given time. And so we really wouldn't have those seasons. And you can hit play and advance through time here. I'm just going to show you a little bit, but you can go ahead and play with this to what would happen to the Earth if we had a different tilt, like that of Uranus or Saturn or Jupiter. So for instance, Venus has a 177-degree tilt. So let's see if we can tilt the Earth almost completely upside down here. Oh, it doesn't look like it's going to quite get me. This would be kind of if it's close to what Uranus is. Let's see if we can get this on the other extreme. And so you can kind of see where those lines would be and how seasons would change based on our tilt. And then if you're in the Southern Hemisphere, you can always change your latitude. Here in Minnesota at the Bell Museum, we're about 45. So we're halfway between the equator and the North Pole. We're kind of a fun location here on the Earth. Let's kind of see how those lines, those blue and purple and green lines, the green line is the equator there, how it changes based on how the Earth is tilted and how the sun rays over in the lower left corner, how the sun would actually come in through our atmosphere. If it comes in more directly, that's kind of like how the sun comes in during the summertime. It gets hotter because the sun's coming more directly into the ground and it gets hotter. But if the sun is coming in at a lower angle here, kind of like now, that's kind of like winter. We're getting the light kind of spread out across the land if it's coming in at a lower angle here, a steeper angle. And so seasons happen on all planets, but it all depends on what their tilt is. And so we'll just be exactly halfway in our tilt between completely towards, the sun in the summertime or away in the wintertime. And that's tomorrow. That's why tomorrow, when we have equal days, equal hours of day and night, that is our spring equinox. Okay. So as it looks like Tad's there working on our telescope, which is awesome that we get to see that view of in the action tonight. That's a new view. We haven't had that before. So that's kind of fun seeing what's happening up on the roof. But another question came in. So just like planets have their own moons, do planets have their own stars? And that answer is no. The only star we have in the solar system is the sun. It's the only one. That's why we all go around it, and that's the only thing we go around. However, if we look out, all the other stars we see at night are so far away from us that no matter where we travel in the solar system, whether it's Mercury or Jupiter or all the way out to Pluto, no matter where we are, because we only have one star in our own solar system, all the other stars are so far away that they will look the exact same. So Orion, 3 stars in a row for a belt, 2 stars for shoulders, 2 stars for knees, will look the same if you're on Earth, on Mars, or on Pluto, because those stars are so far away, we can't tell, or the fact that we're changing location here in our solar system isn't a big enough change to actually see that the stars are kind of lined up a little bit differently. Okay, but let's see here. Some other cool things that are happening. I mentioned that that next to the moon tonight is Mars. So let's go look at our star map again, so we kind of know what we're looking at. Mars here is we're kind of mid to the end of March. It's kind of right here, and it's in Taurus tonight. And Mars is that little orange dot just off to, I'm going to say the right. So we have the curve of the moon tonight. It's on the right-hand side as you look outside. Just off to the west, or just off to the right of the moon, is that little orange dot, which is Mars. And you do not need a telescope to see that tonight. You just need your eyes. And now we're actually about 1 month from something that really exciting happened on Mars last month this time. And that was the Perseverance landing. So our newest rover on Mars. And we're getting gorgeous, gorgeous pictures back from Mars every single day. And so this is a highlight from the past week here. So this image was taken on March 9th. So that is Sol 18, because Mars rotates at a slightly different rate than Earth does. So one day on Mars is about 45 minutes longer than a day on Earth. And that doesn't sound like much, but from one day to the next, it does actually add up. So we don't call them days on Mars, we call them sols. So on Sol 18, or the 18th Martian day, Perseverance took this picture, which is kind of fun because we see the landscape of Mars here, but we also see its robotic arm stretched out front here on the left-hand side. But if you look at the shadow, on one of those shadows here after the kind of middle, more towards the middle of the picture, that's a shadow of this robotic arm. But then the shadow that's all the way over towards the right-hand side of the image, that is its mast cam. So it has the body of the rover, and then sticking up the top is its mast cam with a bunch of cameras there. So with its robotic arm up in this position, it kind of looks like a Perseverance is like cheering itself on, like two arms up in the air, like, yeah, we made it. And so this is kind of a fun picture that came through relatively recently from Mars. And kind of seeing what else is happening here. There's, I think, 23 different cameras on this rover. So here's one kind of that's looking under the rover here. We can see the wheels, and you can kind of see the horizon here on Mars as well in this picture. So this was taken March 13th, so Sol 22, so not too long ago here. There's lots of cool things here about Perseverance. And you can actually track where Perseverance is every day. So we're going to put another link in the chat here, and I'm going to go ahead and switch my screen. And we're going to find out where Perseverance is right now. So hopefully you can see this map here, and the link is in the chat if you want to look it up for yourself. And if I zoom out just a little bit, we can see all of Jezreel Crater. So this crater was chosen for the landing of this rover because it would have been filled up with water. We can tell that because there's a river coming into the crater, and then there's another river going out of the crater. So there's an inlet and an outlet. Now, there's no more liquid water on the surface of this crater. That's why we were able to land a rover and not a boat on Mars. But we can see, if I zoom in just a little bit here, too far, we can see over kind of to the upper left, this river kind of twining in. So this is where we get some more detail, because this is where we wanted to land, right here. So this is the inlet of the crater. But if we look over here to the side, in kind of in the upper right, we have this other little squiggle leaving the crater. And so because we can see there's an inlet and an outlet, we know that this crater at some point in Mars's past filled with water to have water having a constant stream in and out of it. Now, how do we know which? Go for it.
Can I share my screen?
Absolutely, go for it. We'll jump back to the tracking this in a moment.
Totally different thing. Not at all Mars at all.
But it's a telescope, so it's cool. What do we got?
This is 12 million light years away, where we are seeing Messier 81, M81. This very bright area, and it's a little too bright, but the 30-second exposure is working pretty well to get it in view. This is really the bright central core of this absolutely beautiful galaxy. And I'll actually see if I can maybe adjust our histogram and try to actually bring into slightly better view. This is it's one of my favorite galaxies. It's very easy to see, first of all, which is always a big plus. Binoculars can actually pick this one out. It's pretty, in a sense, typical for a galaxy. Many things in the universe, it turns out, are pretty typical of each other. You know, a few 100 million stars in it. It has, though, a close companion galaxy, and really what makes it so easy to see is its companion galaxy M82, or Messier 82, they're gravitationally interacting galaxies. So M81 and 82, their mutual gravitational pull are actually stirring up the gas and dust in each of their own galaxies, and that's causing an immense amount of star formation. So these are galaxies. M81 is a galaxy where we're finding thousands, hundreds of thousands of new stars being born in just this like one point in time, especially over just a few million years. We'll get an immense number of stars born from all this activity going on. So it's easy to see right now, and it'll remain easy to see for quite a while if you all want to go see it yourself, of course.
Can you describe where in the sky this galaxy is?
Yes, and right before I do that, I'll also point out that there's a bit of a smudge as well, and that is actually just dust on our camera, so that's not, it's part of space, but it's very local space. This is also, yes, so it's also easy to find yourself if you look for the Big Dipper. So the Big Dipper, very well-known group of stars, is part of Ursa Major, or the Larger Bear. And if you head up from the two stars in the Big Dipper, and then towards the nose of the bear, M81 and 82 are situated a little bit above the top of the bear, kind of like floating above the bear's eye, if you could imagine there was eye on the bear. It might actually be on our star map. I think I make a point.
It is on our star map. Yes. So if you have that link from the chat and pull that up, the star map on your own screen, or if you want to download the star map for yourself, M81 and 82 are marked on the map, and you can go look at them with your eye or with binoculars. With your eye, it might be hard here in the city, so you have a lot of light pollution.
Yeah, technically it falls within the realm of naked eye visibility, unaided eye visibility, but oof, yeah, dark skies.
Yeah, but it is on the map. It should be fairly easy to find because it is just above the Big Bear. Well, that's really cool because we're coming into the season of galaxies, if you will, and that's kind of a topic we're going to talk way more about next month. But this is a great preview because in the wintertime, we're kind of facing away from the center of our own Milky Way galaxy. And so we can't see as many other galaxies in our sky, but now they're coming into spring. We're kind of, the sky we can see at night has a lot more galaxies in them. And this is a great one because it's near the Big Bear, so it's in our sky all year long. It just, this time of year, it's nice and high in the sky instead of closer to the horizon. And so, like Tad was saying, we do see that bright nucleus, that bright center area of the galaxy here, but the galaxy would kind of spread out around it, kind of fainter, which is really cool. So you might see some kind of haze around it as we see Tad kind of adjusting the exposures and stuff there. There might be kind of a haze around it, and that's the rest of the galaxy. Okay. So this is a really cool image, and I love looking through the telescope. So we're just going to keep this image here, but we have a few more questions coming in about Mars, and so I'll answer those questions as we enjoy this view of this galaxy here that's in our sky. How much does the Perseverance rover weigh? That I don't know. The Perseverance rover is about the size of a minivan, so that gives you kind of a size comparison, but I don't remember how much it actually weighs.
If it's similar to Curiosity, it's no, I do actually do. It's about 2,400 pounds, so about a little over about 2.5 tons.
Okay, there you
go. Very, very similar in everything to Curiosity.
Yeah, it has the same kind of essential frame and basic design of Curiosity, but we've outfitted it, or NASA outfitted it with a lot more cool components like cameras that can actually zoom in, and then it's actually going to collect samples and bring and stash those samples on Mars so we can one day bring them home to Earth. Okay, another question about Mars that came in is, does a day in Mars, the sol, affect or trigger anything? A day on Mars is the same as a day on Earth. It's just how long does it take the planet to rotate once all the way around? And so it just takes Mars about 45-ish minutes longer to rotate once on its axis than Earth. And so that's why a sol on Mars is a little bit longer than a day on Earth. And that's why we refer to it as a sol instead of a day. So we just keep it separate. Are we talking about an Earth day? Or are we talking about a Martian day? So we just call them two different things. But the same effect would happen for a day here on Earth. If you go to Mars, live out your day there or your sol there, you'd see the sun rise in the east and setting in the west. Can galaxies die? This question's coming in from Chris. I don't know that galaxies can die because galaxies are clusters of stars and planets and gas clouds. Tad did say that M81 here and M82, which is nearby, are interacting gravitationally, that is. So galaxies definitely do interact with each other, and they can even collide. And so in that case, if they collide, maybe you could make an argument that they're dying because they'd combine into a new galaxy instead of two separate ones, they'd combine. Eventually, that's what's going to happen to the Milky Way galaxy and the Andromeda galaxy is our two galaxies, which are currently 2.5 million light years apart, if I'm remembering my numbers correctly. And they are gravitationally moving towards each other. Now, it's going to take like 5 billion years for these two galaxies to come close enough to actually merge. But because galaxies are collections of stars and planets and gas clouds, and those things are light years, and a light year is way bigger than a mile, way bigger than any other human-sized measurement, if you will. As we call it a light year, it's a distance light can travel in 1 year. Because there's lots and lots of empty space between those stars and planets and gas clouds, galaxies don't collide hard like two soccer balls hitting each other. What they do is kind of like if my fingers were the stars and the materials in galaxies, as their gravity pulls galaxies together, they just kind of pass by each other. But as they get closer, the gravity between those things gets stronger. And so it starts mixing things up. So it's more like putting everything in a blender and hitting mix. And so everything just kind of gets swirled around based on the gravitational pull as things get closer together. And so galaxies do collide, they do merge. So you can see when a galaxy kind of does that first pass, they'll kind of pass by each other and then they'll get closer and kind of swirl in eventually. Some galaxies have these nice long tails. There's a pair called the antenna galaxy, for instance, and we can see those tails kind of streaming out into space. And that tells us those two galaxies did in fact do a pass by, and they're going to do it again. And it'll take a few million years for two galaxies that have collided, passed by each other and mixed together to kind of settle down into one brand new galaxy. So you could make the argument that galaxies die when they fully combine with another galaxy. Another Mars question. Do we here at the Bell Museum think we'd ever be able to live on Mars or travel there? We're hoping. I think this is not just a Bell Museum staff hope. This is a goal of NASA as well, is that Mars is very different from the Earth. And so it's going to take a lot to make Mars habitable. I've heard some people say that it'd be easier to make the deserts here on Earth habitable than it is to make Mars habitable. Just because it's hard doesn't mean we're not going to try. So we have a goal of getting, or NASA, I should say, has a goal of getting the next man and the first woman to the moon in the Artemis program here in the year 2024. Well, the moon is just a stopping point or a waypoint on to Mars. Now, Mars is way farther away from the Earth than the moon is. So it's going to be a fairly early stopping point, but it's really the only thing that we have on our way to Mars. And so once we get humans safely back to and from the moon here by 2024, 2025-ish, and we get that back under our belt, because we haven't been there since 1972 with the Apollo missions, the next point is to get to Mars. And so parts of the things that we're doing now with the Perseverance rover, one of the instruments on board is it's going to see if it can take some of the atmosphere of Mars and turn it into oxygen that we could breathe. Because Mars does not have a breathable atmosphere for us humans right now. And so we're testing technologies to see what could we do to make Mars habitable for astronauts who are going to go there one day. And so it's a goal. I think we'll get there eventually. I don't know that we'll live there permanently. One person, I don't know if we'll get to be born there and live their lives completely on that planet. That might be a good number of years out, well after my lifespan. But we're hoping to send humans to Mars in the next several decades, I will say. Okay, great questions coming in. Is there water on Mars? Yes, although it's frozen. And so this is a gorgeous view of the moon. I'm going to steal the screen from you, Ted, just for a moment here. And we're going to go back to looking where Perseverance is now, because we can tell there used to be liquid water on the surface of Mars, and we have found with our rovers that there's water under the ground, kind of in permafrost. So we have here Jezreel Crater. I'm hoping you can see this here. We already talked about the inlet and then the outlet, and we know this is where the water flowed into the crater, because if we zoom in a little bit closer, we get better resolution imagery. We can see the river coming in, but then it fans out here. This is a river delta. Much like the river delta, the Mississippi flows down and then it empties into the Gulf of Mexico, we get this kind of fan shape in the Gulf of Mexico. That's the Mississippi River Delta. And so we see the same structure on Mars that tells us this was created by running liquid water. And so this blue circle was the target area of where Perseverance, we want it to land. And if we zoom in even more, and so this is on that link that we shared with you a little while back, we can see exactly where Perseverance has traveled in the past month. And so we can see all these points. So it started over here on Sol 0 on the very first day. And then about 2 weeks after it landed, it made a short journey. And then it can actually travel here. And we can see this map, which is kind of fun to see where it's traveled. We can see how far it's traveled from point to point. And so right now up at the top of the screen here, you can see on Sol 23, it's traveled about 0.06 of a mile. So it hasn't driven all that far, but we are tracking exactly where it is. and where it's been. So you can actually trace that out here. And you can see it kind of doubled back a little bit here on its most recent journey of its leg here. Eventually, what it's going to try to do is go explore that river delta. So we're a little bit further away. We landed something that was a little bit flatter. It landed something that's flatter. So it's going to drive over here and explore this river delta. We're all a bunch of rock. And hopefully we're going to find something that tells us that life was living in that water at one point in time, would have settled down to the ground as it came out of that river at one point in time in Mars's past. So we know Mars had water on it in its past, and we know that there's water in the permafrost on Mars under the ground and the polar ice caps. And we have some observations that say that there's underground lakes on Mars. But if that data really is indicative of a liquid lake, that lake would have to be extremely, extremely salty to still be liquid on Mars right now, way saltier than our oceans. I'll send it back to you, Tad. I just want to make sure everybody kind of could see that crater detail of where Perseverance has landed. I know we're coming up close to the end of our time together tonight, so I want to get to a few more questions. It looks like we have about 4 minutes left. If there's anything else, I'll just turn over the camera to you, Tad, as I go through the questions and answers here. What are the temperatures on Mars? Jen is asking. This is a great question. And Tad did something that was really cool in our planetarium. So Perseverance and Curiosity and Insight are the three robots on the surface of Mars right now that are currently working, that are NASA's. They're sending us weather data all the time. So each day. I don't remember what the temperature on Mars was today, but Tad built this really cool thing into our planetarium where we can pull up that information from these rovers during our planetarium shows and share that with you. Now, Mars has seasons much like Earth does, so it'll have its winter and it's colder and it's summer when it's warmer. I believe the full range of temperatures near the equator, I think in the summertime, it can get to maybe 70, 80 degrees, which is a nice nice summer day here in Minnesota. But that's going to be on the hot range of of Mars's temperature spectrum. Mars is typically going to be much colder than Earth is. So it's going to be like minus 119. And it can get much, much colder. So if you want to know the temperatures, you can explore the website that we linked to. I'm sure that along with where the rover is today, it'll also tell you weather details. But she also comes to the planetarium, and we can show you that too, because Tad built that really cool thing into our planetarium shows. How does Perseverance navigate since there is no GPS? Well, this is a really cool thing that it does because it's an upgrade from Curiosity. Now, because Mars is so far away, it takes time for the signal to get from Earth to Mars, and then Perseverance says, okay, yeah, I understand that instruction you just typed me, and it sends a confirmation back to us here on Earth. And so we used to have to tell Curiosity, which landed in 2012, where to go. And it would do its move, and then it would tell us, okay, I did it, now what should I do? Perseverance here, though, has some capabilities to figure that stuff out for itself. Now, it's not driving completely on its own because people here on Earth are still telling it what to do. It's managed by JPL, part of NASA. But it has some capabilities to decide where it's going to go, if it's go to the left or to the right, kind of over an obstacle or really big rock, if you will. So Perseverance has some capacities to drive itself, which is really, really cool. And it actually can go much faster than Curiosity ever could. So we're still driving it nice and slowly because we don't want to drive it over a really sharp rock or drive it over something where it would tip sideways. So we still have to be very careful of where we tell it to go. But it's a very, very, very interesting rover, and one that has a lot of capabilities even on its own. How deep are the craters on Mars? Katie, I'm not quite sure how deep some of the craters are on Mars, but I do know the tallest mountain in the entire solar system is on Mars. That is Olympus Mons. So Mars has topography much like Earth does, high mountains, low valleys. It has a great canyon, much, much bigger than our Grand Canyon. That's Valles Marineris. I'm not quite sure how deep that particular canyon goes. So there's lots of really cool geology and topography on Mars as well. But we are just about out of time. Oh, yes, go for it.
For everyone who's been wondering what this weird thing is on their screen, this little fuzzy dot, this is the Cat's Eye Nebula, or Caldwell 6. It's a rather stunning example of a planetary nebula, which represents the death of a star. So as we reach the end of our time tonight, well, all things must end. And that joke for the end too, right?
Even
Um,
stars have to die. Yep.
yeah, and this is an incredibly intricate nebula. Our camera's picking up really just the basic structure of it, this elongated oval structure, which is actually represents, this is the outer atmosphere of the star. So is this star probably about the size of our sun, in fact, an average size star. As it reached the end of its life, the outer layers puffed off, kind of like almost like a dandelion going to seed. The outer layers kind of float off in a sense into space as the star expands. And we're seeing that. But then the very core of the star is still emitting energy, and that actually heats up that outer atmosphere. It causes it to emit light. So we're seeing the dead atmosphere of the star powered by the still glowing core of the original star that's there.
Very cool. And that one is, granted, we can see these really cool things from our roof here at the Bell Museum and our telescopes. But if you do ever look up the Cat's Eye Nebula through like the Hubble Space Telescope, you'll see all that intricate detail that Tab was just talking about. We just don't have access to the Hubble Space Telescope. That's all. But I do want to say thank you for joining us tonight. Next month, we are going to be talking about galaxies. So we got a hint of that tonight, talking about M81 and M82. Next month, we are going to be joined by Laura Salo. She's from the university's Minnesota Institute for Astrophysics. She's working on her PhD studying galaxies. So that's what we're going to be talking about next month on April 16th. But thank you all for joining us tonight. The Star Parties and astronomy programs couldn't be possible without you. And Ruth and John Huss are big supporters of our astronomy programs. Gifts of any size have a huge impact on our ability to bring programs like this to you. Thank you so much for joining us on this Friday night with some wonderful weather out. Go look at the moon, and we'll see you next month, everyone. Thanks for being here.